Large language models, they feel incredibly powerful these days. They can draft emails, brainstorm, even write pretty decent code.
Oh, absolutely. The capabilities are amazing.
But then you try to get them to answer something really specific, maybe about a super niche topic or something really
Right.
cutting edge,
Yeah,
and you can almost feel them like stumble. It's like their knowledge just stops at whenever they were last trained.
that's exactly it. Their knowledge is, well, vast, sure, but it's fundamentally static. It lacks the depth and the real-time currency you need for a lot of specialized fields.
Right. And that's the problem that retrieval augmented generation, or RAG, is supposed to tackle, isn't it? That
Mhm.
first layer of trying to give LLMs access to stuff outside their training data.
Precisely. It's that first step,
Mm.
giving them dynamic external information.
So, like, instead of just digging through its own memory, the RAG system basically tells the LLM, hang on, let me check this external knowledge source first.
Yep.
It goes and finds relevant documents or data chunks and then uses that retrieved info to actually generate the answer.
Exactly. And, the traditional ways of doing this RAG often rely on things like dense vector similarity.
Finding stuff with similar meaning.
Right, finding text chunks whose meaning seems close to your query, or sometimes just simple keyword matching.
Which seems fine, I guess, for finding, like, relevant documents or paragraphs, maybe?
It can be, yeah.
But what if your question needs more? What if you need to understand how different facts link together? Connect person A to discovery B and then to impact C.
Hmm.
Can traditional RAG, which is maybe looking at isolated text snippets, really get those structured relationships? It feels like it would struggle.
It absolutely struggles with that. That's the gap, the precise gap that GraphRAG tries to fill.
GraphRAG, okay.
Yeah, so the idea here is representing knowledge not just as loose text, but as a structured graph. You have entities, you have relationships connecting them, like a semantic network.
So it's more like giving the LLM a map of the knowledge, not just a pile of books.
That's a great analogy, yeah. And that richer, structured context should, in theory, allow for more sophisticated reasoning.
Okay, sounds good in theory. Very promising. But I'm guessing building and actually using these GraphRAG systems isn't like a walk in the park. The paper we're looking at flags some pretty big challenges.
Oh, definitely not straightforward. For one thing, the engineering is notoriously complex. You've got all these stages, extracting the entities, building the graph, processing the query, the retrieval itself, generation, maybe verification.
Wow, okay. Lots of moving parts.
Tons. And trying to figure out which part is the bottleneck or how tweaking one stage messes up another, it's really hard to isolate the effects.
Yeah, I can see that. And then there's this evaluation problem you mentioned. How do you even know if the system is really using the graph knowledge effectively?
Right, or is the LLM just sort of falling back on stuff it already half knew from its massive training data?
Especially if the benchmarks you're using to test it. If that info was probably already floating around in the LLM's training soup.
It's a huge issue, a critical point. The paper actually gives a pretty stark example of this later on. They show how a standard LLM can look like it's doing great on a benchmark.
But it's not really the retrieval.
Potentially not. It might just be recalling data it saw during pre-training, which makes judging the RAD part of the system incredibly tricky. You think your graph retrieval is working wonders, but maybe it's just memory.
Okay, that's a major headache for evaluation. And the last thing you mentioned was query decomposition, getting the system to understand the question properly.
Yeah, that's another major bottleneck. If the system takes your complex natural language question and messes up translating it into something that can actually query the knowledge graph effectively.
The whole thing goes off the rails right at the start.
Pretty much. If the interpretation of intent is wrong early on, the retrieval will likely be flawed, no matter how good the graph is.
Okay, so we've got LLMs lacking deep current knowledge. We've got basic RAG helping a bit, but missing relationships. And then GraphRAG offers structure, but gets bogged down by engineering complexity, evaluation fuzziness, and these query problems.
That's the landscape, yeah. And it's exactly this set of challenges that led the researchers to develop ROGRAG.
ROGRAG. Okay, what's the acronym stand for?
The paper calls it a framework for robustly optimized GraphRAG.
Robustly optimized. Got it.
Yeah, it's basically their systematic attempt to tackle these specific issues we've just laid out.
All right, mission set then. Let's unpack this paper. We're doing a deep dive into ROGRAG, figure out exactly how it tries to solve these problems, what its framework actually looks like, and, what the key innovations and findings are.
Sounds good. So let's circle back to that core problem just to ground ourselves again. LLMs are fantastic pattern matchers, right? But they're not dynamic knowledge bases.
They're like those brilliant students who only read books published up to, say, 2022. Ask them about something brand new or super obscure.
And they're basically making educated guesses or just saying, I don't know.
Which is why R is so crucial. It's like literally sending the LLM to the library for a quick fact check on current or specialized stuff before it answers.
Exactly. But as we said, the standard R retrieval often just looks for keywords or general semantic similarity. It might find a paragraph mentioning Marie Curie and another mentioning radium.
But it doesn't explicitly hand the LLM the structured fact, Marie Curie discovered radium.
Right. It doesn't give it that subject-predicate-object structure.
Yeah.
And that's where using these explicit entity relationship graphs is supposed to help. The graph knows Marie Curie is a person, radium is an element, and there's this discovered link between them.
That structure should theoretically allow for deeper reasoning.
That's the hope.
Got it. But turning theory into practice hits those snags. Building a pipeline that works reliably involves all these interacting parts. Hard to debug, hard to tune.
Yeah, figuring out what change actually led to an improvement is tough.
And that evaluation problem you mentioned, the benchmark overlap issue. Can you give that example again?
Sure. So the paper talks about this, referencing their Table 1. They tested a 7B parameter model against ground truth answers on a specific dataset subset, ultra-domain. And in some cases, using another LLM as a judge, the model's RAG output was actually preferred over the ground truth answer.
Wait, the model beat the ground truth. How?
Well, it doesn't necessarily mean the model is smarter. It strongly suggests the model might just be recalling answers or phrasing styles it saw a lot during its pre-training because that benchmark data was likely part of it. So the judge LLM thinks, oh, this looks like a good answer, but it might be memory, not effective retrieval.
Wow. So the benchmark itself can completely mislead you. That's critical.
It really is.
Okay, and then the query part again. If the first step is asking the LLM to translate my complicated question into graph operations, and it gets that translation wrong.
Yeah, the whole retrieval process downstream is likely compromised from the get-go. Garbage in, garbage out, essentially.
So, ROGRAG. It's designed to navigate all this. And you said it showed some pretty significant improvements.
That's what the paper reports. On a knowledge-intensive dataset called SeedBench, they specifically picked this one. They apparently boosted a 7B model score from a baseline of about 60% up to 75%.
15% jump, that's substantial. And they picked SeedBench because the base LLM wasn't already acing it.
Exactly. That helps isolate the effect of the RAG system itself. If the base model already knew all the answers, you wouldn't know if your fancy retrieval was actually doing anything useful.
Makes sense. So ROGRAG achieves this by, what, combining things?
Basically, yeah.
Yeah.
It integrates and refines ideas and best practices from several previous GraphRAG approaches. Things focused on scalability, simplicity, reasoning, robustness, pulling them into one unified framework.
Okay, so the big picture sounds like a unified framework, maybe supporting incremental graph building, a much fancier retrieval system that uses multiple tricks, and this focus on really rigorous evaluation using datasets where you can actually see the RAG effect.
That's a good summary. So let's dive into the methodology. How do they actually build the knowledge graph, the indexing part?
Right.
You start with your text corpus, your documents, you process them, clean them up, maybe segment them into manageable chunks. Then the system uses an LLM to try and extract key information.
Like what?
Entities, people, places, things, relationships between them, keywords, maybe short descriptions. And it structures these as triplets. Think subject, predicate, object. Like our example, our Marie Curie discovered radium.
Okay, so it pulls out these structured facts,
Yeah.
and then those triplets become the graph.
Essentially, yeah. The entities become nodes, the relationships become edges connecting them, and crucially, these graph elements are linked back to the original text chunks they came from.
Got it. And for that extraction step, they use something called loop NER strategies. What's that about?
Right, NER is named entity recognition, but here they expand it to relationships too. It's basically an iterative process. They use the LLM in a loop, potentially refining the extraction process over multiple passes.
Okay. And this is where you found that slightly weird result in their analysis.
Yeah, this was genuinely surprising looking at their Table 3. They compared different ways of doing this extraction loop, and the fascinating finding was that simply increasing the total number of nodes and edges they extracted, even if some of those extracted things were actually wrong.
Wait, extracting wrong stuff helped?
It correlated positively with better accuracy in the final system. It feels totally backwards, right?
Yeah. How does that work?
So the paper's hypothesis is pretty interesting. They think these incorrect entities or relationships often end up as isolated nodes or small disconnected bits in the graph. They add noise, sure, but they don't really mess with the main correct structure that's actually useful for retrieval.
Uh-huh.
Meanwhile, the push to just extract more stuff, overall, also manages to capture more correct entities and relationships, strengthening the useful parts of the graph. So the benefit of getting more good stuff outweighs the downside of some isolated bad stuff.
Okay, so optimizing the LLM prompt helps reduce the errors, but sheer quantity up to a point seemed beneficial even with some noise.
That seemed to be the finding. More data, even noisy data, potentially being better than less, cleaner data in this context.
Wild. Okay, that's a really unexpected insight. So once you have this graph, potentially with some noisy bits, how does ROGRAG actually get the relevant info out when I ask a question? The retrieval part.
Okay, yeah, this is where it gets, I think, really interesting. Because ROGRAG doesn't just rely on one single retrieval method, it uses a multi-stage approach, which they show in their figure 2.
Multi-stage.
Yeah, your query comes in. An LLM first analyzes it to figure out the intent, and then the system can actually deploy 2 different main retrieval strategies.
2 strategies running, or it picks one.
It can use both, or fall back from one to the other. Let's break it down. Strategy 1 is called the dual level method. That's in their figure 4.
Dual level, what are the levels?
It breaks down your query into sort of low-level keywords, often the entities involved, and then higher-level relational descriptions like the what and the how they relate.
Okay.
And then it tries to match both of these levels against the knowledge graph.
How does it do the matching? Is it exact?
No, and this is key. It uses fuzzy matching, not just strict, do these words match exactly? It looks for similar terms, variations, and it applies this fuzzy matching at different granularities, matching entities, relationships, maybe combinations.
Right. And the reason for doing this fuzzy dual level thing.
Robustness, mainly.
Yeah.
Real-world user queries are messy.
Right.
People use synonyms, phrase things awkwardly, maybe imply relationships instead of stating them clearly. This fuzzy, multi-granularity approach makes the system much better at finding relevant parts of the graph, even if the query isn't perfectly phrased. It boosts the retrieval coverage.
Okay, so that gives it flexibility. What's the second strategy then?
The second one is the logic form method. This is outlined in their algorithm too. This is quite different. It's inspired by more structured reasoning frameworks.
Logic form. Sounds more formal.
It is. It uses a predefined set of logical operators. Things like filtering nodes based on properties, traversing specific relationship edges, maybe performing aggregations like counting or summing.
So instead of just matching fuzzy keywords, it tries to turn my English question into a series of logical steps, like a mini program for querying the graph.
Exactly. The LLM tries to transform the natural language query into a sequence of these formal operations.
Okay.
Then the system executes those operations against the graph step by step to retrieve the context.
And why add this more complex logical method? What's the benefit?
Well, it tends to provide higher information density in the retrieved context.
Mm-hmm.
Because it's following specific logical paths, it pulls out very targeted nodes and edges. Also, the paper notes that domain experts often prefer this method because the steps are clearer and more interpretable. You can sort of follow the system's reasoning.
Ah, I see. And maybe better for certain types of questions.
Definitely. It's particularly good for questions that require calculations. How much taller is X than Y? Or complex multi-step reasoning that the fuzzier dual-level method just isn't built for.
Gotcha. So one is flexible and robust, the other is structured and precise. How does ROGRAG actually use them? Does it run both?
It prioritizes the logic form. It tries that first. The LLM attempts to convert the query into that logical sequence.
But what if it fails? Like the question is too ambiguous or something?
Exactly. If the LLM can't produce a valid logic form, or if a later verification step flags the results from the logic form as insufficient, then it gracefully degrades. It falls back to using the dual-level fuzzy matching method instead.
Oh, clever. So it tries for the precise method first, but has the robust fuzzy method as a backup.
Precisely. It ensures the system stays robust and can usually provide some relevant context, even if the more complex logical approach doesn't pan out. It also enables things like streaming responses faster.
Nice fallback mechanism. Okay, you mentioned verification again. How does ROGRAG check if the retrieved info is any good or if the final answer is right?
Yeah, verification is another key component. They use an LLM, a separate check basically, to assess either the retrieved context or the final generated answer. And the paper compares 2 main ways of doing this, detailed in their algorithm 4. They call them argument checking and result checking.
Argument checking versus result checking. What's the difference there?
So argument checking happens before the final answer is generated. The LLM looks at the user's question and the context retrieved from the graph and asks, is this context actually sufficient and relevant to answer the question?
Okay, checking the ingredients before cooking.
Exactly. Result checking, on the other hand, happens after the system has already generated an answer. It looks at the original question, the retrieved context, and the final generated response all together, and tries to judge if the whole thing is coherent and correct.
Checking the final dish. So which one worked better? You mentioned another interesting finding here, right, from table 7.
Yeah, another slightly counterintuitive one. They found that argument checking the context before generation, was actually preferred and performed better in terms of accuracy for verification. It scored 0.75 accuracy compared to 0.72 for result checking.
Huh. So checking the ingredients is better than checking the final dish in this case. Why would that be? Feels like looking at the final answer would give you more information.
It does feel that way. But the paper suggests a couple of reasons why argument checking might be superior here. One idea is that when the verifier LLM looks at the generated response along with everything else, that generated response itself might act as a distractor. It could bias the LLM's judgment.
Ah, the answer might unduly influence the check.
Potentially. The other point they make is about the type of LLM they used, a causal model. They argue that if the input context is actually sufficient and correct, then the reasoning process the LLM uses to generate the answer from that context is also highly likely to be correct. So, verifying the context effectively pre-validates the subsequent reasoning and result, making the later result check somewhat redundant and potentially noisier.
That's fascinating. So focus the LLM verifier on the quality of the source material it's working with, rather than getting it potentially sidetracked by the output it generated itself.
That seems to be the takeaway, yeah. A really neat insight into how these models behave in verification tasks.
Okay, let's talk more about the experiments. You said they use SeedBench heavily.
Right, SeedBench. It's domain-specific agriculture curated by experts, and crucially, standard LLMs don't do well on it out of the box. That makes it a great test bed for seeing if their ag part is actually adding value.
And the headline result was that big jump, 60% to 75% accuracy for their 7B model using ROGRAG.
Yep, that was the main claim. And they also showed it outperforming other approaches like standard LangChain RX setup, classic BM25 keyword search, and another GraphRAG method called RQRAG across different metrics like accuracy and F1 score.
And the ablation studies, where they tweak different parts. We touched on some findings already.
We did, like confirming from Table 3 that, yeah, more extracted nodes and edges, even with errors, seem to help accuracy, up to a point.
And that weird finding about context length for the extraction LLM.
Yeah, from Table 4, using shorter context windows like 32K context versus 64K actually gave them better entity extraction results.
Counterintuitive again. You'd think more context would help it understand.
You would, but their suggestion is maybe too much text in one go makes the specific task of pinpointing entities and relations harder for the LLM. More noise than signal, perhaps.
Interesting. More isn't always better, at least for that specific task. What else did the ablations reveal about the retrieval methods?
Table 6 really highlighted that trade-off we discussed between dual-level and logic form. The dual-level fuzzy matching had higher overall test accuracy, particularly for simpler fact retrieval.
Okay.
But the logic form, even if its raw accuracy score was sometimes lower in these tests, was strongly preferred by the domain experts. They liked that the answers were more structured, the logic was clearer, and the information density was higher. And critically, only logic form could handle those calculation-type questions.
So that really drives home why having both strategies and the fallback mechanism is so important. You need the fuzzy matching for broad coverage and robustness, but you need the logical approach for precision, interpretability, and certain types of reasoning.
Absolutely essential to combine them. And related to this, their tests on representation and matching granularity, shown in Table 5, kind of sealed the deal.
What did those show?
They found that making the query representation richer, like using a longer context window during retrieval, 28K here, boosted accuracy by 4%, helped. Expanding the set of keywords used in the dual-level fuzzy matching also helped. But switching to strict exact matching, getting rid of the fuzziness, that significantly hurt performance.
Okay, so pulling all that together.
It really hammers home the point that flexible fuzzy matching is absolutely crucial for dealing with the messiness and nuance of real human language queries. It confirms the value of that dual-level approach as a necessary foundation or complement to the more rigid logic form.
It definitely sounds like a lot of careful tuning and smart design choices went into ROGRAG, learning from these experiments. And you mentioned this isn't just a lab experiment.
That's right. The paper makes a point of saying the OGRAG framework is actually deployed. It's running on an online platform called SeedLLM, which serves as a Q&A system for agricultural knowledge.
Cool, so it's out there in the wild. Okay, this has been a fantastic deep dive. Let me try and summarize the key takeaways for you listening. ROGRAG looks like a really solid attempt to build more practical, effective GraphRAG system.
Mm.
It tackles head-on those big challenges, the engineering complexity, the unreliable evaluation, the tricky query processing. Its main innovations seem to be this unified framework pulling together best practices, and especially that clever multi-stage retrieval. It smartly blends the robust, fuzzy, dual-level method with the precise, structured logic form method using a fallback so you get the best of both worlds. Plus, adding verification with that interesting finding that checking the input context beforehand seems better than checking the final result.
Yeah, that covers the highlights. And the paper is commendably upfront about the limitations too, which is good to see.
Right. What were the main ones?
Well, the results presented are mostly based on one specific LLM, that Quinn 2.57b instruct model, and primarily tested on that one domain-specific dataset, SeedBench.
Yeah.
So generalizability is still a question. Building a truly perfect, universally reliable verifier component, that remains a tough challenge. They also acknowledge that errors can still propagate. If the initial entity extraction messes up or the query decomposition goes wrong, later stages might not be able to recover fully. And that query decomposition, especially translating natural language into the logic form steps, it still relies on heuristics and the LLM's interpretation, which remains a potential bottleneck.
Oh, fair points. Things to keep working on.
So,
But it leaves us with a really interesting thought to chew on based on their findings, doesn't it?
which one are you thinking of?
The logic form versus dual level trade-off. If the logic form method, the one the human experts liked more because it was clear, logical, structured, and could handle calculations, sometimes scored lower on the automated accuracy tests compared to the fuzzier dual level approach. What does that tell you?
Yeah, that's a great question.
What does it say about how we're evaluating these complex reasoning AI systems? Are our current metrics, like raw accuracy, capturing everything that matters? Or is there immense value in human interpretability in a clear logical process, even if it doesn't perfectly top the leaderboard on a specific benchmark?
It's a classic tension: performance versus interpretability. The paper does suggest future work on improving the verifiers and the decomposition, which might help align those expert preferences with the test scores better. But it's definitely something for all of us to think about as these systems get more complex. How do we measure success?